Hi guys, there are a couple more Doppler problems. We're going to do number 26 and 27. Two submarines are underwater and are approaching each other head-on. Sub A has a speed of 12 meters per second. B has a speed of 8 meters per second. A sends out a 1515 hertz sonar signal that travels at a speed of 1522 meters per second in salt water. What is the frequency of the sonar signal detected by sub B? So here goes nothing. I have a submarine, so let's draw a fancy sub. Let's call this submarine A, and I have sub B. Okay, maybe I'm not drawing fancy subs. So submarine A is going forward at 12 meters per second, and sub B has a speed of 8 meters per second, and these are going towards each other. Sub A is sending out a signal, so the frequency of the source is 1550 hertz. That travels at a speed, the velocity of the wave in salt water is 1522 meters per second. I want to know what is the frequency of the sonar signal detected by sub B. So sub B is my listener. I want to know what frequency is observed by B. That's my big question mark. This one's a little bit more confusing than some of the other Doppler problems we've done because we've got a different medium. We've got water, salt water, and we have two things in motion. So let's take a look at our equation and plug some things in. So the frequency observed is the frequency of the source times the velocity of the wave plus minus the velocity of the observer, velocity of the wave minus plus the velocity of the source. Now the neat thing about this equation is if you pay attention to the approaching or minus or going away from each other, you don't have to change signs if things are going away or towards. Just use the convention of what's going on here. Because of the fact that sub A and sub B are actually both moving towards each other, which set of signs are we going to use? The top or the bottom? We're going to use the top. So it's plus on top and minus on the bottom. That's what we're going to use because these two subs are headed towards each other. So let's see if we can pull all the pieces together here. So the frequency observed is the frequency of the source, 1550 hertz. The velocity of the wave, sound in salt water on this day, is 1522 meters per second. They're going towards each other. That's going to be a positive sign. The velocity of the observer. Okay, sub B is my observer, and it is moving at 8. I apologize for not in the problem putting more sig figs in. 8 meters per second. The velocity of the wave is 1522. Okay, that is the speed of sound in salt water, minus, because of the situation, the velocity of the source. The source is the speed of sub A, 12 meters per second. Now let's take our time and do this carefully so we do not make a boo-boo. All right, so top half of the fraction is going to look like 1522 plus 8. This is going to give me 1530 meters per second. 1522 minus 12, this is going to give me 1510 meters per second. These units are going to cancel, so I'll end up with hertz. So now I'm going to do 1530 divided by 1510, multiply that by the original sound, 1550, and I get a frequency that is observed of 1571 or 1570 hertz, depending upon how you round off. If we round off to 3 sig figs, I guess it's 1570. That's the observed frequency heard by sub number B. Number B, sorry about that. Okay, let's do another one of these. This Doppler problem is a little trickier because we're going to be solving for a velocity. So here goes. A car at rest, a car's horn sounds the note concert A, 440 hertz. The horn is sounded while the car is moving down the street. A bicycle is moving toward the car at 1/3 the car's speed, and here's a frequency of 475 hertz. What is the speed of the car? This one's a little trickier. We don't know the speed of either the bicyclist or the car, but we know the ratio between them is 1/3. So here's what's going on. We have a source. Here's my source. And my source is traveling down the street at some unknown velocity. We do not know what that velocity is, and it's got its car horn going out at 440 hertz, concert A. We have a cyclist, here's my little cyclist, that is bicycling down the road towards the car, and its velocity is 1/3 V. And it is hearing the frequency that is observed. Frequency that is observed is 475 hertz. I want to solve for V. This 440 is the frequency of the source. So let's take a look at our equation and see what we can do. Frequency observed, frequency of the source, velocity of the wave plus minus velocity of the observer, velocity of the wave minus plus velocity of the source. Okay, first off, is this going to be which set are we going to use, top or bottom? Bicyclist and the car are moving towards each other. Because they are moving towards, this is going to be the top set, so that's the set of plus and minuses we're going to use. The frequency that is observed is, let me change back to a darker pen here. Frequency observed is 475 hertz. The frequency of the source is 440 hertz. The velocity of the sound on this day, we're not told anything, so when in doubt, go with 343 meters per second. It's an approach, so this is going to be positive. Velocity of the observer is going to be 1/3 V. Let's turn that into a decimal, 0.33 repeating V. And then down below, velocity of sound minus velocity of the source, V. All right, now we get to do some fancy schmancy algebra to make this all work. First thing I'm going to do is I am going to divide both sides by 440. So if I divide both sides by 440, divide this side by 440 hertz, divide that side by 440 hertz, that's going to cancel. This is all going to turn into 1.08 equals all of that, 343 meters per second, plus 0.33 repeating V divided by 343 minus V. And we're trying to solve for V. So what are we going to do next? Because we got to get things out of the basement. Next thing I'm going to do is I'm going to divide both sides by 343 meters per second minus V. So 343 meters per second minus V, V, E, that's going to cancel that. And I'm going to end up with 1.08 times 343 meters per second minus V equals 343 meters per second plus 0.33 repeating V. Okay, distributive property. Remember that old distributive property? This has got to be distributed through. Also multiply this times that, this times that. So I'm going to grab a calculator. 1.08. 1.08 times 343 is 370 meters per second minus 1.08 V is 343 meters per second plus 0.33 V. I've got to get like things together. So I am going to add 1.08 V to both sides. and I am going to subtract 343 meters per second from both sides. This is going to cancel, that's going to cancel. What I'm going to end up with is going to be 370 minus 343. This is going to give me 27 meters per second. The other side, I'm going to end up with 0.33 plus 1.08. I'm going to end up with 1.41 v. And so my velocity is going to be 27 meters per second divided by 1.41. 27 divided by 1.41. I did my math wrong. Sorry, hit my calculator buttons wrong. And I end up with the velocity of the car as 19.1 meters per second, 19.1 meters per second. And that makes sense. How fast is that? That's 45-ish miles per hour. That's a logical answer for a velocity of a car. All right, that will do. This is a trickier Doppler problem. It's not that bad, but the algebra you have to take some time with. See you next time. Bye-bye.